Now the electric field is just a constant. The potential difference, delta V, would be minus E dot dl from point P1 to point P2. Well, since the electric field is just a constant, you can just take it out of the integral. Minus E dot P1 to P2 dl. Well, this is just the sum of the displacements, the net displacement that you go from P1 to P2. You can just imagine any path you like. This will be just E dot R2 minus R1. R being the position vectors of these points. This will be minus, well, the electric field is 3 and 7 volts per meter times R2 minus R1 is minus 1, minus 2 meters. Meters, they will just cancel. So this will be minus 3, minus 14 volts. This is 17 volts. Well, there are many ways of solving this question. This is the answer. You should get. This is just constant. It is pointing always in the same direction and has the same magnitude. No, it's not, it doesn't depend on x and y. These are x hat and y hat. They are just directions. How many? I mean, you will see when I read it. Other questions? Why the magnitudes? We want? I mean, we have to deal with the direction somehow. The volt doesn't depend on the direction, but of course it depends on the electric field, the direction of the electric field, and how your points are oriented. It depends on those things. Okay, so? Okay, then you have to multiply with the cosine of the angle between the two. And this should be your answer. One thing you should note, it doesn't have any x hats or y hats, for example. It's not a vector itself. It doesn't have any direction. You're right. So it should go from P2 to P1. True. You can deduce points from my solution. Other questions on this one? Okay, so today we will be starting a new subject. I mean, last week we started about discussing the force that the magnetic field creates, but we didn't really discuss what creates the magnetic field. So today and on Thursday, we will be discussing what creates the magnetic field. And then eventually, well, this is mainly for the next chapter, but just to give you an idea of what you should expect, I mean, where we are heading. Well, this is just an aluminum tube. And here you have just two masses. They are more or less the same weight. So let's see. How long should it take for this mass to fall down? Well, this is, let's say, 1.5 meters. Okay, so let's see. How long should it last? 1 second. It should be less than 1 second. I mean, something like 0.7 seconds or so. So let's say if you drop it, it just falls down almost right away. If you drop it, it falls down almost right away. There's some friction, and hence it will slow down. Now let's try with the other one. It came down. Well, this is one thing that we should understand. It will take less than 2 weeks. And after 2 weeks, we can come back to this example. So at least there should be some force acting on it. I mean, if it is falling only due to the effect of the gravitational force, it should take less than 1 second. And we had seen that at least in this sample, it does take quite short to fall down. But with this one, how long does it take? Can you time it, somebody? Start. Stop. Okay, it's something around 8 or 9 seconds. Now, what is this additional force? Now, we had already seen that the magnetic field exerts a force on currents, and hence currents exert a force on magnets. This is a magnet. These two are magnets. This is not a magnet. So being a magnet just changes this time. Now, how does it happen? Now, that again we will discuss in a couple of weeks. We know that already currents will exert a force on this magnet. That is one possible explanation, but then the question is, what is creating the current? There's no battery over here. But as you will be testing also in your experiments this week, this is a magnet, so if you just let it go through your tube, there is a changing magnetic field lines are moving, and hence they will create a current. You can try it, just wait. So here we have another setup. Sorry? This is aluminum. It's not a magnetic material. Magnets do not stick to aluminum. I think it's aluminum, right? It doesn't stick to it. It also doesn't stick to these ones. Hmm? It's not an interesting site. These are not magnets. Now, these are not magnets. These are just rings. But there should be one more. Here we have this coil. And we will see today that these coils, current-carrying coils, they are creating magnetic field. So let's see what happens. Nothing happens. Okay, so let's try with another one. This is lighter. I think this is the lightest of them. And there's the fourth one. Nothing happens. I'm playing with them is fun. I don't know about watching them, but so let's see. We don't have any magnets here. That is, in that demonstration we had magnets. One of them was a magnet. But in this one we have no magnets. We have a coil over here. The coil will be creating the magnetic field, as we will start studying this hour. Okay, so here we have a magnetic field. And then we have these things which are not magnetic, which are just conductors. And the fourth one, which didn't work, the difference of this fourth one from the other ones, I mean, these are made of of different materials, but they're all conductors. They have that thing in common. This is the difference of this one from the other ones is there's a cut over here. It's not a complete ring. So why does it change the behavior completely? There's nothing over here. Might be. And we have this jumping thing. Now we will discuss what happens. And as a last example, this is more relevant to the experiment that you will be doing this week. Okay. There's no battery here. I just put it over here, turn it on, and then we get the light. The only thing we have over here is this this coil. Just like in today's experiment, in this week's experiment, you will be just letting a coil fall through, a magnet fall through a coil. It will be creating a time-dependent magnetic field, a changing magnetic field. And here we have this, this coil creates this changing magnetic field, and then we have another coil over here. This should go through. Okay. And let's see what happens if you remove this. So it is still on. There's still some light coming out, but it's very weak. So another question that we should be answering is, what is this? Now it should be iron. I mean, why does iron have such an effect? What is the effect of the iron? Well, if there was some current, I mean, to have such a significant effect, it's likely that there's a huge current, I would have been electrocuted. I was holding this thing. So there's probably not that much of a current. Well, it is, by the way, if you just look at it through, it is made of iron, but it's not pure iron. If you look at it through, you will see that it has a circular cross-section. And inside you have small circles. Now, each one of these circles is iron. And they are, I'm assuming that they are insulated from each other, so they don't short circuit. So what is the effect of this thing? Now, these are the things that we will be discussing in the next few weeks, and these are the things that you should have in mind when you are preparing your pre-reports. And this is where we will be heading. Now, any questions about what we have done until now? Not about these demos. We will be discussing these demos in the future classes also. But anything else you want to ask before we start a new subject? Well, we will understand in a couple of weeks. No, I will not answer that yet. In a couple of weeks. I mean, these demos, we will study them in the next couple of weeks. We will discuss why it happens. Now, those are the things that you should keep in mind. You should look forward to the explanations of these. You should try. Sure, come now. This one. Well, you can ask her to try it. Which one would you like to try?
The lightest one.
This should be the lightest one. No. Well, we have to wait. It's heated up. You will try it at the end of the lecture. Okay, so now let's start discussing. We have discussed the effects of the magnetic field. It exerts a force on moving charges, on current carrying wires. Now let's discuss the sources of the magnetic field. Well, first of all, let's just remember what the force was. Now, this is the force that a charged object feels in the presence of a magnetic field. Now, the magnetic force is always related with the velocity. So you have a magnetic force only if you have charges that are moving. Well, the same thing holds for a magnetic field itself. You get a magnetic field only if the charges are moving. So you can basically say that the source of the magnetic field is not the charge itself, but charge times the velocity. The source of the electric field was point charges. Whether the charges moved or not, they created an electric field. But in the case of the magnetic field, it just turns out that the source of magnetic field is moving charges. For any object, as long as there are moving charges, it creates a magnetic field. Even for the magnet. Of course, for the magnet, there is no current in the sense that there is no current running inside. But the atoms themselves, if you imagine the atoms themselves, the atoms are made up of moving charges. So basically, moving charges are everywhere. So everything creates some kind of a magnetic field. But in certain materials, the magnetic fields created by different atoms making the system, they just cancel each other. In certain other materials, they do not cancel so readily. You have to work hard. Okay, so we already have one place where we can study moving. Now, one problem with studying the magnetic force is, in general, the strength of the magnetic force is much weaker than the strength of the electric force. Electric force is much stronger than the magnetic force for typical systems. But if there's no electric field, then you can feel the presence of the magnetic field. Now, one place where there are moving charges, whereas there's no electric field, is current carrying wires. Now, the wire itself is neutral. The plus and the minus charges, they just cancel each other. So there's no electric field created by a wire. But nevertheless, since there are moving charges, and it's only one type of charge, minus charges are moving, they will create in a metal, let's say, it's the negative charges that are moving, so they will create a magnetic field. The positive charges, although they cancel the electric field, since they are not moving, they will not create a magnetic field. So if we have a wire, let's first start with a straight wire. Let's say we have a current running in this direction. The magnetic field created at some point, it has a magnitude mu0 over 2 pi I over r. Now, how do we know that measurement? We will be discussing a more basic relation than this one, but for the time being, let's just assume that this is our result. If you have a uniform straight wire, this will be the magnetic field that it creates. Now here, mu0 is 4 pi times 10 to the power minus 7. What's the unit of mu0? What should be the unit of mu0? Tesla meters per ampere. What is Tesla? What's the unit of Tesla? How can we express it in terms of other units? Well, you see, we have this expression, force is equal to QE plus V cross B. So the unit of E, for example, this is newtons per Coulomb. The unit of B, which we defined it to be Tesla, is, just look at this expression, the magnetic field is force divided by Coulomb, and we should also divide by the velocity, which has units meters per second. This is the unit Tesla. This is 1 Tesla. Newtons per Coulomb, meters per second. So for example, if you are solving a problem, you get a result in which you are adding something that has the units of Tesla with something that has the units of Newton, then you can tell just by looking at your result that what you have done is wrong. You should always check your results for their consistencies. You cannot add quantities of different units. So it's important to know, at least for that thing, it's important to know what how the different units are related to each other. And what about the direction of the magnetic field? This is just the magnitude, and the direction is determined by the right-hand rule. Wrap your fingers around the wire such that your thumb points in the direction of the current. In that case, your fingers show you the direction of the magnetic field. Now, in this case, the magnetic field lines will be just circles around this wire. Of course, they are everywhere. These are the magnetic field lines. So now we have a source of a magnetic field. And if there's a magnetic field, if you put some current next to it in that magnetic field, then the current will feel a force. Let's do an example. Here we have a wire, here we have another wire. Both are carrying currents I1 and I2, and they are separated by a distance d. What is the force per unit length that each wire feels? Now, first let's calculate, no, this is I2. The force that the first wire feels. Now, we already know what the force acting on a wire is if we put it in a magnetic field. If you remember this, the force was given by, well, let's say dF. A very small segment of the wire will feel a force B, no, I times dl cross B, I1. So this is, we have a wire that is carrying a current I1, and we are considering a very small segment of the wire that we show by dl1, dl. dl, the direction of dl is in the direction of the current itself, and B is the magnetic field where we have this dl. So along this wire, if you just say that this is our dl, what will be the direction of this force? Okay, so first of all, what is the direction of the magnetic field along this wire due to this one? Wrap your fingers, the magnetic field is pointing towards you. This is the B over there. So what is the direction of this dF? This is dl, your fingers in the direction of dl, your palm facing the direction of the magnetic field, your thumb is in the direction of dl cross B. So the force that this will feel is in this direction. This is the F1. F1 will be just the sum of all these segments, but I1 is just constant. B along this wire, since they are parallel, B will be constant along this wire everywhere for all the segments along this wire. So if we summing all these DFs is nothing but summing all these DLs. And when we sum the DLs, at least let's say for the magnitude, all the forces are pointing in the same direction, so we can just add the magnitudes, and the magnitude of the F1 will be I1 L times B. This is for a length L. So the force per unit length is I1 times B. Now we already know what B is. The magnitude of B, we have this infinite wire. We were already told that it is mu0 over 2 pi times I over R. Now in this case it is D, the current is I2. This is the expression we have. It's mu0 over 2 pi I over R. Now you see this R over here is the distance from the wire, not from a fixed point on the wire. Now this wire will feel a force due to the magnetic field created by the other wire. Of course, it depends on D. But you see, since these wires are parallel, all these small segments on this wire are at the same distance from my second wire. So D is always the same. This is the, all of them are D. Now the strength of my magnetic field at this point and at this point, they are the same, because this D is this distance from the wire itself, not from a one point on the wire. Over here. Well, the magnetic field is everywhere, but the current is only here. You see, if you look at this, if you would like to use this expression, the current running through, well, your friend has a, okay, let's just add that one. I can define some DL over here. There is nothing that prevents it. I can define this DL. There is a magnetic field also over there. But what is the current? There's no current running through that. It's empty. Yes. It's only this wire feels the force. Now, this magnetic field, now in this example at least, we are interested in this problem. We have these two wires, and nothing else. Both of those wires are carrying a force, carrying some current. Now, in this case, they will be feeling a force, mainly because each one of these wires, this wire, for example, will create a magnetic field at the position of this wire. Since there's a magnetic field, there's a current running through it, it will feel a force, only due to this second wire. Yes. Now, let's see, in this case, well, let's discuss it afterwards. Let's finish discussing this question and ask that question, okay? Then we will discuss how do we determine the poles of this magnet. No, they are infinitely large. Now, I'm just assuming as a length L and calculating the force that this segment feels. And eventually what I'm interested in is F1 over L. This is I1, and B is I2 mu0 over 2 pi d. This is the force per unit length. Now, of course, in real life, we don't have these infinitely long wires. But if the wires are sufficiently close to each other, and if they are long compared to their separation, this formula will be more or less still valid. Of course, there will be some deviations towards the edges, but if the edges are small compared to the total size, then this will still give you a good result. other questions? Okay, any other questions on this one? I will discuss that in a moment. Mhm. Okay, let's discuss that. How does the magnetic field lines look like? Let's say we have this I1 and this I2. And we also know that the magnetic field line of a single infinitely long straight wire, the magnitude is mu0 over 2 pi I over d, I over r. R being the distance from the wire. So you just take your point, draw a vertical line to your wire, and that distance is what we call the R. Now, close to this wire, let's say, let's look at close to this wire. What is the dominant contribution to the magnetic field, the I1 or I2? I'm very close to this wire. Well, let's see, they are separated by a distance d. The magnetic field created by I2 will be proportional to 1 over d. But the magnetic field created due to I1 will be a 1 over very small number. So close to I1, the magnetic field lines are given by the magnetic field lines of I1 only, which are nothing but circles. So close to I1, these are our magnetic field lines. Similarly, close to I2, these are our magnetic field lines. But then as you are going away from the wires, the magnetic field lines will feel the effect of the other one. So they will start to be deformed. You will get magnetic field lines like this, and eventually like this. Somewhere over here, you will get something like this. These are how the magnetic field lines will look like. Why should they? These are not equipotential surfaces. No, they don't intersect. Well, can we define a potential? First, let's ask that question. We will ask that in a couple of minutes. Now, let's go back to this example. Now, do you agree that this is the force per unit length? So what we did, we already know the force expression, we know the magnetic field expression. So this wire will feel a force due to this other wire. I mean, you can just think of it as you have 2 point charges, for example. If you have 2 point charges, each charge feels a force due to the presence of the other charge. Now here we are talking about 2 currents. Each current will feel a force due to the other current. And the force that each current will feel will depend on the magnetic field created by the other current. And this force per unit length is given by the product of the currents times this coefficient over here, which depends on the inverse to the distance. This is our magnetic field. Now let's just assume I1 is equal to I2, which is equal to 1 ampere, and the distance is 1 meter. Then the force per unit length will be, remember, this is I1 times I2 mu 0 over 2 pi times d, which is equal to 1 ampere squared. Now mu 0 was 4 pi times 10 to the power minus 7 Tesla, the unit, Tesla meters per ampere, times 1 over 1 meter divided by 2 pi. 2 pi times 1 meter. So let's see, the meters, they cancel. This ampere cancels one of this one. This is equal to 2 times 10 to the power minus 7 Tesla times ampere. Is this the correct unit? You see, the force have to be newtons. Now we found something Tesla amperes. Now this should be newtons per meter, sorry. This is the force per length, so this should be newtons per meter. Is Tesla amperes meters, newtons per meter? Yes. Newtons per meter. The units are correct. In fact, this is the definition of the ampere. Now, we didn't really precisely define the Coulomb. We said that, okay, one electron is 1.9 times 10, 1.6 times 10 to the power 19 coulombs, but I mean, that's not a practical definition that we can use. Here we have a practical definition of ampere. You just take two wires that carry the same current, and you just separate them by 1 meter, and you measure the force per unit length. You increase the current until the force per unit length is nothing but 2 times 10 to the power minus 7 newtons per meter. You just fix it to this value, and the current you have is just 1 ampere. This is how we define 1 ampere. And once we have the 1 ampere, 1 coulomb, 1 coulomb is nothing but 1 ampere times 1 second. And this is how we actually define the coulomb now. And that is also why this number over here, you see, I didn't write an approximately equal to 4 pi times 10 to the power minus 7. I said exactly equal to 4 pi times 10 to the power minus 7. Because this is the definition of mu 0. We are not measuring mu 0. We define mu 0 to have this value, and using this definition of mu 0, we are defining ampere. We are measuring ampere. And once we measure 1 ampere, we can measure 1 coulomb. It's just like the speed of light. Speed of light is not measured. It is defined to be a fixed value. And using that definition of the speed of light, we measure 1 meter. And just like that, here, mu 0 is a coefficient that we define to have this value. Using this definition, we define the ampere and we define the coulomb. Using this definition, we measure the ampere. You cannot. Because you are defining this thing, this number, and measuring everything else using this number. So if you try to measure this number and find something different, in that case, that means that your equipment is not properly calibrated. You are measuring wrong things. Yes. Well, it's not just one person just comes out and say, okay, let's define it like this. But historically, okay, of course we had this concept of the meter, we have the concept of some concept of the Coulomb, etc. But then when they measured this mu0, what they have seen is that mu0 over 4 pi was something very close to 10 to the power minus 7. And then, of course, everybody agreed to define mu0 like this. You see, you have many things. You have to define the ampere, you have to define the Coulomb, you have to define this mu0, etc. And you can just change the definition of single one of them, and nothing would change if you make a corresponding change in some other variables. So they are all dependent on each other. So you are free to choose any one of them to have any specific value. And some people chose this to have this value. For example, I prefer to choose mu0 to be just 4 pi. Fine, use whichever unit you like. You just invent some other unit for Tesla, but you see the definition of Tesla also depends on other factors. You see, Tesla is not just an arbitrary unit. Tesla is defined in terms of newtons. Well, you cannot change the definition of newtons. Seconds, meters, but they're already fixed already. And Coulomb, but the definition of Coulomb is determined by the definition of the ampere. So once you measure ampere, you cannot change Coulomb. So the definition of Tesla is already fixed by your choice of mu0. So once you choose mu0, you already fix what 1 Tesla is, the magnitude of 1 Tesla. For example, the magnetic field on the surface of the Earth. B on Earth, it is something close to 10 to the power minus 4 Tesla. If you measure the magnetic field close to the Earth, this is what you will obtain. And we had made the definition that this is 1 Gauss. We just defined some new unit. And 1 Gauss is 10 to the power minus 4 Tesla. Of course, so that's why I write approximately. In some places maybe it's 0.5, in other places 2 Gauss, but in some places it will be minus 0.5 Gauss, it will be pointing in some places it will be pointing outward, in some places it will be pointing inward, but the magnitude is typically of this order of magnitude. And that is what we define 1 Gauss. If you measure it close to a magnet, it might be even larger, but typically of that order of magnitude. I mean, if somebody asks you what is the weight of a human being, you would probably say something around 70 kilos. Of course, some human beings are like 3 kilos when they are born. Some get as heavy as 500 kilos, but typically it will be 70 kilos. The magnetic field on Earth typically has a magnitude 10 to the power minus 4 Tesla. Well, it is this mu0 is called the permeability. Why? Just wait a bit. Does it permit magnetic field? Kind of. Penetrate, permeability, they all come from the same root, as far as I know. Anyway, so, any last questions? See you on Thursday.